Modelling, we know now, is embedded right through and has its own substrand for each of the three main strands. Number and algebra is one, measurement and geometry is one, and also for probability and statistics. So with plenty of development around the country, and in particular, much work done in Queensland with modelling and with the Australian curriculum, the authorities in WA have extended this research and have decided to make it explicit that this should be taught across the curriculum. A common language has been developed with words like analyse, represent, solve, determine, interpret, communicate, and so on. And these are explicitly mentioned throughout the curriculum. You may not be able to read this, but you can see these words appearing in the content descriptors for Western Australia. The keywords are there, and you can see the horizontal development. Each of the content descriptors start with in real-world situations involving whole numbers, positive fractions, and then they are expected to be able to analyse, interpret, represent, and communicate. So this is a key part of the WA curriculum. Now, I have an example of a potential modelling task, which is also being printed into your booklet. And this key modelling task is one from Year 10, Cambridge, that I've selected, and we'll just do a small activity on this in a minute. But a modelling task is essentially a problem where mathematics is used to describe the problem and explore and come up with a solution. So a context is provided, and a preliminary task is a low-level or low-floor context building activity to strengthen both mathematical readiness and contextual understanding without preempting the modelling strategies. So this particular modelling task asks students to think about an impassable object like a gorge or a river or a road, something that they would like to find the distance across without actually going into that area. So with this preliminary task, students are asked to place pebbles or find trees and measure the distances between them in such a way that they're lined up as two triangles. And I'm pretty sure everyone knows which area of mathematics this relates to. But working through that, they'll be able to build their understanding of similar triangles and think about the mathematics that they might use in a modelling context. Then when they get to the actual task, they're required to choose an object, like a road or a river or a ravine that they can get to, and then consider, as part of the modelling process where they're analysing and representing, is where they're going to consider possible placements of the pebbles or rocks or trees or whatever it might be to create the two similar triangles, and then take the measurements. So they're modelling the situation and they're drawing diagrams, taking measurements, and creating something that they might be able to use mathematics with. Then, to solve, they would prove and confirm that the triangles are similar, determine a scale factor, and then solve the problem by using that scale factor to determine or estimate the river, the distance across the river or the ravine. Now, I actually did this activity with my Year 10s only last week, and they coped quite well with that. But when we got to interpret and verify, I could tell that there was an added challenge to this, because interpreting and then verifying in this modelling situation could mean that they rearrange their pebbles for the same situation, have different measurements, but hopefully come up with very similar answers to the distance across. And that was a really big step for many students in my class, realising that it didn't matter how they originally placed the pebbles, provided they created similar triangles, they could confirm the distance across the road or the driveway or whatever they chose. So the interpretation and the verification was fairly complex part of this modelling activity. And to finish, they had to write all that up and communicate that in a report. Something that was readable, cohesive, and had all the solutions and diagrams and a photo as well of their activities. There are some extension questions there as well. But let's do a little bit of modelling ourselves on that activity. So what would be the most common error a student would make when trying to prove that those triangles are similar? What would the error be? Yeah, thinking it's RHS because there's a right angle there. But there's only one pair of corresponding sides. So RHS needs two, and all the other ones need two as well. So there are, obviously we have vertically opposite angles and a couple of corresponding angles as well. So AA, AAA is the proof. That particular example is from one of the chapters at Year 10, and we'll talk a little bit about modelling later when we talk about some of the new resources that Cambridge are going to offer. So modelling is in the curriculum, and it's something that we've tried to focus on at Cambridge for a number of years now. I mentioned the modelling before, and while we created some of these modelling activities for Queensland and with the research that they've done, and also for the Australian Curriculum Series, these have been adapted for the Western Australian curriculum with the correct language used as recommended, using words like analyse, represent, solve, interpret, verify, and communicate. You may not be able to read this. This is another example where students are modelling a cylindrical park seat where there's a fixed amount of concrete and they're looking at this surface area and how much space is going to be painted, and looking at the relationship between the radius and the height and considering how much surface area there is if they change that relationship on the fixed volume. Just talking about modelling a little bit more, you can see that modelling task is set up in a certain way. It's been written so there's a realistic chance that even if a teacher did not prepare for the lesson, there's a chance that it could be successful. So there's that warm-up preliminary task, and there's a reasonably highly scaffolded modelling task and some extension questions. But we also understand that there are other ways of thinking about modelling. And so one of the tasks that we've added to the list is a re-engineered modelling task for Western Australia, where we still have the preliminary task, but there's a new section called Working with Models. And in this section, we're explicitly aligning with the WA's modelling phases, providing clear metacognitive clues where students are engaged with partially constructed models or build them step by step. Now you'll find an example of what we've done on the next page of your booklet, where you can see one of the Year 7 modelling tasks has been re-engineered with these new sections. The preliminary task is still there, but the next section, Working with Models, takes those key words from the Western Australian curriculum, and we ask students very specifically to do these things, to think about what is happening with the modelling process in this particular context. Following that, there's a very clear scaffolded modelling task, and then at the end, a similar task that is completely unscaffolded. So this is more open-ended and unscaffolded. And we believe this is somewhat similar to what might be in the text as an experience, but offers an alternative to modelling tasks for teachers and their students. Scott, were there any other motivations for recreating some of the modelling tasks in this way?
Yeah, so there is a variety of views about how to teach modelling, especially at the younger levels. Now, you may teach year 11 and 12 courses and would be familiar with the mathematical thinking process and the statistical investigation process and the language that is used or expected by SCASA in a successful student response, and the ability to recognize that there are simplification is necessary as part of the modeling, mathematical modeling of the real world, and hence there are assumptions that are made and students need to be aware of those assumptions. Think about the technology that they're using, all of these different things. And there are challenges with perhaps reflecting those expectations at the younger year levels. So the activity that you're looking at there is for year 7, but it still allows for some fairly explicit discussion of the fact that there are assumptions and what are assumptions and all those kinds of things, even going back to year 7. So SCASA is very keen to see the steps of the modelling cycle taught explicitly to your students, even going back to year 7. So we have developed these additional activities. They'll be available in the teacher resources to download. Rubrics will be provided, all of these kinds of things that reflect the kind of language that's not only in the WA curriculum, but also in the mathematical thinking tasks, the exemplars that SCASA provide at year 11 and 12, to allow those discussions to get your students used to seeing activities that are like this, so that by the time they get to year 11, that they should be fairly familiar with this kind of mathematics.
There are 10 modelling activities for every series. There's one for every chapter. Now, one may not expect to get through 10 modelling activities in a year, because you might be doing other things as well. But a modelling activity has been written for every single chapter right across the series. So that's 40 of them in the Cambridge 70-point series. There are also another 40 activities which come under the Digital Tools and Computational Thinking banner, which is new to the series. And the WA curriculum has clearly tried to modernise the curriculum and include words like digital tools, 32 times, in fact, if you count them. This connects well to the current technologies and modern applications of mathematics and computational thinking. And you can see that definition there, that computational thinking is a way of solving problems that involves breaking them down to smaller parts and identifying patterns and developing step-by-step instructions. And this has strong connections with the new Australian curriculum and what's been going on in Victoria, for example, as well. And so there is a recognition around the country that many of the problems that we are solving in industry these days are solved not necessarily with Euclidean and geometry or algebra skills, but they're solved computationally, where potentially an algorithm is being used, or technology is being used in such a way to find a solution where algebra is not being used, where problems are so complex that we zoom into the answer rather than trying to solve it exactly. And this is reflected in many of the world's competitions, including over here in WA, which probably has some of the best students in the country with the computational and algorithmic thinking competition run by the Australian Maths Trust, and the informatics competition, which are very quickly becoming more popular than mathematics competitions. And this has been recognised around the country, in Australian curriculum, in other countries as well. And so problems that can be solved computationally are starting to appear in the mathematics curriculum. And so to react to that, we have written 40 investigations connecting to the content of each of the chapters.
Maybe we could do for 30 seconds, maybe you could talk to the person next to you and have a discussion about whether computational thinking is or is not in the WA curriculum? What do we think? Yes, yes or no? What's the answer, David?
I think both.
Yes.
Both would be the answer, because the word algorithm and the word computation is perhaps not there, but there's clearly an understanding that it exists, and this is an influence. And the word digital tools comes in so often that I believe the curriculum is encouraging us to start to think this way. So using technology, using spreadsheets, graphing calculators, finding numerical solutions, doing simulations in statistics and probability, this all fits under the banner of computational thinking. And I think a lot of us have always been doing it. Like when we use the bisection method to solve an equation, for example, at year 11 or year 12, or we are finding an intersection point using graphing software, not an algebraic solution, is essentially solving a problem numerically. And so this is something that is creeping into our curriculum, and we're hoping that people will enjoy the computational and digital tool activities that we have in every one of the chapters. In fact, we have a little activity now, and this is in your booklet as well. We've just printed one off from year 7. It's called Soccer in the Rain. And this is one of our digital tools and computational thinking activities. And we're going to do this now using a spreadsheet. And so that is an estimate of the probability that we'll be playing at least 7 matches in a season. Now, for those people who are more advanced with their probability, you'll probably know that this is a binomial distribution. But by using simulation and a very simple little bit of Excel code, we're using computational thinking. We're introducing students to these ideas, and we're using technology to solve problems like this without necessarily going to a really high level of maths.